Okay, so by the way, the running time of this function, this recursive function, is going to be proportional to this to the number being computed, right? So in particular, the running time is going to be this, which is going to be 2 to the n over square root n, of, right? So I'm just mentioning it as a random aside. Okay, but we want to solve the question, which is on a different issue, which is how many distinct calls do we get? So let's look on the top parameter, right? T, right? We call with n, right? What happens in the recursive call? Well, we decrease n by 1, but the bottom of the recursion is when t equals 0, right? So the first parameter t can be 0, 1, 2, all the way to n, right? So there are n plus 1 options on this. Okay, what about the parameter b? Well, b can also be either 0, 1, or all the way to t, but t is at most n, so it can be, in fact, b can be all the way from 0 to n. One needs to convince oneself that the recursive call t is always going to be smaller than b. So this is indeed true. So this is another n plus 1 values. And as such, if you multiply them, we get n square distinct calls, because we are using the notation. Note that this is, in fact, a bit conservative, because then the right number is probably something like n squared over 2, because you're not taking values where b is bigger than t, right? So if you look on the matrix of those values, you're getting only half of it. But we don't care, right? We want only the asymptotic notation, so we get O of n squared, right? So this is the interesting thing, right? Because the number of distinct call is quadratic, but the running time is awful. It's exponential. As I said, 2 to the n roughly over square root n. So not happy days. Okay, let's move on to the next question. Okay, so now we are looking in the memoized version. And the question is what is the running time? So to analyze this, you need to do, you need to think about what is going to happen, right? So what is going to happen is that we're going to have this matrix, n by n matrix, right? And then we're going to ask to compute this value, the n over 2, right? If you want to think about, here I'm thinking about the explicit memorization, which in fact, the code here is not clear whether it's, well, it's written as implicit, but it also can be used as explicit in this case. Anyway, right, what happened is that now, so this is the B, this is the B, and this is the, this is T, right? This is T, and this is B. Okay, so now what's happening is that we are calling on T minus 1, right? And T minus 1 and B, right? So this is going to call recursively on computing those two values here, right? And so it continues, right? Essentially, you're going to get this whole area being computed where, every cell is going to ask for the values in the two values next to it, right? So you're filling essentially this portion of the matrix. Okay. Now, when you fill an entry, think about the recursive call, right? When we're filling an entry, what are we doing? So let's relook at this, right? Zoom in. We have a cell that we are currently computing, recursive call. We call recursively to compute those two other values, this one and this one, which we assume the recursive function just do it in constant time. We are ignoring the time that the recursive calls cost us. This is how you analyze it. So if you ignore the cost of those two recursive calls, then of course you get a number back from those two recursive calls, and then you have to add them, and you add this up back. So filling this entry costs us constant time. constant amount of work, right? And we are filling up quadratic number of cells of n square because we saw that this is the number of distinct recursive color. If you want, this is the number of values that are going to be stored in the dictionary data structures. So as such, the overall running time of this procedure is quadratic, right? So this is the amazing thing. The amazing thing is that by just doing memorization, suddenly we reduced an exponential running time to polynomial running time. In fact, it's a reasonably good polynomial running time, which is quite good. Okay, this was the answer to the two questions.